Now, under this arterial supply to the heart, when we have the greatest flow through those coronary arteries, because remember, arteries is taking the blood away from the heart, that flow is greatest when the heart relaxes. So the contraction of the myocardium, which is the cardiac muscle, that will compress those arteries and stop the blood flow. But when the aortic valve opens and we can have that blood begin to flow, we're going to see that that relaxes and doesn't press on those arteries. So when we have this contraction and the relaxation of the heart, that's going to actually be when we have our blood for the coronary circulation be the greatest. Now, when blood flows, the veins will return it to the heart. So when we look at the drainage of the veins, well, basically, organs are going to use the blood, tissues are going to use the blood, and the bloods return, okay? When the blood returns, it's going to return to the right atrium. Now, in the coronary circulation, that blood flow to the heart itself, the way that we get venous return to the atria by way of this coronary circulation, there is an area called the coronary sinus. Now, if you remember your terminology, a coronary, I should say a sinus. A sinus is like a hole, okay? This hole. And when we begin to look at the coronary sinus, we're going to find that the great cardiac, the posterior interventricular, and the left marginal veins are going to feed into this coronary sinus. That great cardiac vein, this one is going to be collecting blood from the anterior portion of the heart, and it will empty into that coronary sinus. The middle cardiac is going to collect from the posterior portion and drain into the coronary sinus. And then the left marginal, from the left margin of the heart, moves into the coronary sinus. So those three veins are going to make their way into this place, this spot, this hole called the coronary sinus. So what that's going to be able to do, the coronary sinus, as the blood collects at this area, at this hole, it's going to be able, or it's going to have basically a direct connection to empty into the right atrium. So not only does all the blood that gets used by the organs and the tissues and everything else in the body empty into the right atrium, but the coronary circulation itself is going to empty into the right atrium. Now, the cardiac muscle, the structure of that cardiac muscle, well, this takes us all the way back to part 1 when we were looking at tissues. And we had a slide that had skeletal muscle, smooth muscle, and cardiac muscle. And the cardiac muscle was interesting. It looked a lot like skeletal muscle, but the difference was it had only one nucleus per one cell, and it contained intercalated discs. So when we talk about the structure of cardiac muscle, that one cell we're going to refer to as a cardiocyte. When cardiac muscle has damage from heart attacks, okay? The only way that it can heal is by fibrosis. Once the blood supply to the cardiac muscle has been cut off, the cardiac muscle does not return. So the only healing that can occur is to bypass that tissue, or that tissue doesn't work, well, the tissue is not going to work either way because it becomes fibrotic. And if it becomes fibrotic, it can't function. Now, those intercalated discs, if you remember, intercalated discs were found from cell to cell to cell in the cardiac muscle. One of the interesting things about an intercalated disc is they interdigitate. And if you interdigitate, it looks like something like this. Okay, so it looks like they do this overlapping for the intercalated discs. So what we're going to find is we're going to have those interdigitating folds. We'll have some junctions, either mechanical or electrical. And by the contact that it has, the structure that it has, that's going to be able to increase the surface area. Now, we have to increase that surface area, okay, because we need to have the passage of materials occur quickly. And if you remember, when we talked about the contraction of muscle, we need sodium, we need potassium, we need calcium, we need a lot of ions. So we're going to have to make sure that these materials can flow quickly between the cells. When we talk about the mechanical junctions are to hold those cardiac cells tightly together. So they're going to have something called fascia adherens. Just simply means to adhere, okay? And so you're going to have a linking from cell to cell to cell. And then, I'm not sure if you guys remember, but in part 1, we talked about desmosomes and those structures where one can be, half of it can be in one cell, half can be in the other, and they can meet and they can hold cells together. So we need to have those cells, and those cells are held together very tightly by way of these mechanical junctions. The electrical junctions, these are going to be gap junctions. Now, the reason that they're termed electrical is because they allow ions to flow. This means we are going to get to be able to pass this action potential in these cardiac cells. So when we talk about the heart beating, when the heart beats, it looks like it does it in one swift move, but in actuality, it's each one of those cells functioning together and each one doing its job. So it's a coordinated effort, but every cell is basically working independently. This is a view, if you can remember, from the slides in AMP1. These are the cardiac cells. Very similar because it looks like it's striated, okay, to skeletal, but the cardiac is cell to cell. And those margins are going to be these intercalated discs. And they're trying to show how they digitate, okay? And then down here, if we take a peek, they're letting us see the gap junctions that will exist so that we can have that flow of ions for the electricity, the potential to pass through those gap junctions. When we talk about the metabolism, the homeostasis of the cardiac muscles, let's face it, they have to have aerobic respiration. The last thing that the heart can do is depend or carry out fermentation. It can't do it because the cells are so dependent on the energy, and let's face it, they're beating all the time. I mean, if that heart stops, hello, the organism stops. Okay, so in the heart muscle, they have some molecules that are very rich. They are rich in myoglobin and glycogen, and there's a huge amount of aerobic respiration that is carried out. The mitochondria in the heart are huge. It can adapt to other sources for the aerobic respiration. Now, in the case of oxygen lack, okay, we're going to definitely see that a lack of oxygen affects the heart very quickly. Luckily, our heart is pretty much fatigue resistant because it pretty much, I mean, it's going to carry out the aerobic respiration. And the only time it's going to fatigue and quit is when you die. I mean, it doesn't matter what happens. Your ultimate cause of death is your heart stops. Okay? Doesn't matter if it was cancer or another disease or whatever. The ultimate cause of death is your heart stops. Now, the heart, when we talk about the beating of the heart, we have what's called the conduction system. And we have the heartbeat, and we have what's called an internal pacemaker. And then we're going to have some conduction pathways. And what this will do is it's going to regulate the heartbeat. And the last thing the heart depends on is the nervous system to beat. Okay? It has its own pacemaker. So in the heart, we have what's called the SA node. The SA node is basically some modified cardiocytes, and it will determine your heart rate. And it initiates each heartbeat. The pacemaker is going to be found, this SA node, it's going to be found in the right atrium. And when this signal gets started, in other words, when that SA node fires, that signal is going to spread. So what we're going to see is that when the SA node fires, it will spread through the atria first. Now note that I'm saying it's in the right atrium, but when I said it spreads, I said atria, so that means right and left. So the SA node will fire. And once we have that fire, the next is the AV node. This is a node that's near the right atrioventricular valve, and this is the way that we're going to pass this electrical potential to the ventricles. Now, we have what's going to be termed the bundle of His, and this is the atrioventricular bundle, and that's going to be something that will fork to the right on the ventricle and to the left on the ventricle. And it does this by way of bundle branches. And then the branches, they will move towards the apex of the heart. Now, in this structure, we're going to have what's termed Purkinje fibers. These are going to be the little extensions from this bundle of His that spread throughout the myocardium. And what it's going to be able to do, it's going to have those cardiocytes, which is that muscle cell, pass that signal from cell to cell to cell by way of those gap junctions.